So we're going to talk about lesson 67. We'll be able to create and use momentum. So what we were to calculate and use momentum. Now, there's going to be a fair bit of time us spending talking about what momentum is, and then there's going to be a little bit of time spent calculating it. But yeah, momentum in many ways is a tool, and it's a new useful way for us to start to think about motion, but also to think about forces as well. And we're going to deal with that in a fair bit, probably on Monday's lesson, but we're going to start today anyway. Okay. So before we go forward to talk about momentum, let's go backwards just to wrap up what we were talking about last couple of lessons. The last couple of lessons have been talking about Newton's second law in two dimensions. The first way to do that was to talk about what happens when two connected objects pull on each other, what happens when one of those connected objects pulls on the other one, but it just so happens that it's pulling on it because of gravity, which was turned out to be exactly the same types of calculations. The only difference was that because there was more forces acting on this object, we had to deal with, like, because there was friction acting on this object and the force was caused by just the train, we had to factor those in. Then what we did was we looked at what happens when you take two blocks and you push the two blocks, very, very similar to the connected objects with the train cards. But it's only a little bit different because we were sort of like saying, well, we can now, again, do the same force diagrams. If this pushes on this, what forces will it experience as a system, and then what forces will it experience as two or more bodies. And then we sort of wrap this up by talking about an inclined plane. The trick with an inclined plane is that the gravitational force is not parallel with the surface. So what we had to do was we had to find a way to make it parallel. And what we did is we learned how, we'll go back to here, we learned how we can turn the gravitational force, we can break it into a component that is parallel to the surface and a component that is perpendicular to the surface. And then we did a question on that as an attendance question. We did this question too, where we looked at a coffee on a roof of a car, and we said, well, you know, how much is it going to slide? We said it's like it's sitting on the hood of the car, a well-polished car, it starts to slide down, because the reason it starts to slide down is because this force hit here, and we had to calculate that force. Then we did the same thing with a frictional force of a car on a hill. Then I gave you guys some questions to do. Now, that was 10.6. So I haven't given you anywhere to upload those yet, so I will do that too. So that means I'm going to give you a place to upload 10.3, 4, 5, and 6. So you guys can start taking photos of your stuff and putting it on Compass. And I'm going to, on Classroom. I'll give you guys some time to do that as well. Momentum. Oh, there's a question. Sorry, before we move on. So did you upload a checklist on Compass or Google Classroom? So I haven't uploaded a checklist yet, no. So all I've done so far is I've usually just said for 10.2, 3, 4, and 5, I was just said to do all of them. There was only 10.6 that I sort of said, right, you're gonna have to do all the questions, because I wanted you to focus on some of them. So I haven't made a checklist per se, but I can maybe put one together over the weekend and put it online for you to access. Let's talk about momentum. What is momentum? Momentum is similar to inertia. Inertia describes an object's resistance to a change in motion. We talked about inertia when we talked about Newton's first law, whereas momentum describes how much motion it has. Momentum is a way to describe if an object, so if inertia says how much does it not want to change, and momentum says, well, if it's moving, how much is it moving? How much, it describes, momentum gives a definition of how much motion something has. Now I might say, but sir, isn't that just what velocity? Isn't velocity and speed how much motion something has? And I can only give you an airy-fairy answer, which is to say, yes, velocity does give an idea of motion. It says, well, uh, velocity says how quickly something's changing its position, but momentum is a bit more than that. Momentum is not just how quickly something's changed its position, but also what mass it has. Because when you think about motion of objects, right? If I think, when I think about a motion of an object, I'm thinking about a ship, a massive freighter ship, like a huge ship weighing hundreds and thousands of kilograms, hundreds of thousands of tons, and that ship is moving at 1 meter per second. And then I take something like a snail that's moving at 1 meter per second. Yeah, sure, they both have the same velocity, but they don't really have the same motion, in that they're not really the same thing. If I put my foot in, like, between a snail and a rock, I'm not going to be that afraid for my foot, even though that snail is going at a massive 1 meter per second. But if I put my foot in the path of a ship, and that ship is going like, and that ship happens to be going at, like, I don't know, 1 meter per second, but that ship is huge, I'm talking about, massive ship, then I'm going to be kind of worried, because I'm like, that ship is going to crush my foot because it's so big. And that's sort of the difference here. We need a way to kind of connect those ideas, to look past we need a way to look past, when we talk about motion, to look past the idea of how fast it's going, but also we need to tie in, well, how much mass does it have? How, like, when we talk about motion, we want to know, well, what is it? It's not just a small snail. Is it a small snail that can easily have its motion stopped? Or is it a massive ship that's going to struggle to have its motion stopped? And that's where we get to the difference here. Now, how do you calculate momentum? So momentum is equal to, and the symbol we use for momentum is P. Oopsies. The symbol we use for momentum is P. And how you calculate momentum is mass times velocity. Nice and easy, no complicated stuff here. Because velocity is a vector quantity, guess what? Momentum is also going to be a vector quantity. The arrow on top of the P and the V is a representation of it being a vector. That's what the thing is. Now you might say, again, it's that same sort of thing. You can see now why we have an issue with, using the same letters. So we're using P to represent momentum because M is already used for mass. So P represents momentum. And so when you say, and a lot of you guys probably have used the word momentum before, you may not have, but a lot of people use the word momentum before in, in just general descriptions, like, oh yeah, he crashed into him and his momentum caused the other person to fall over. That's usually when we use the word momentum. Momentum is more than just the speed of something. When you say, oh, the momentum is almost like how much energy that person has when they're moving at a certain speed. So I've got a picture here on the right of a train, because a train has got a large amount of momentum. It's moving a large mass at a very high speed. So we can calculate that as momentum. If that train crashes into something else, it's going to pass its momentum to another object. And we're going to talk about that briefly as well. But this is a general formula of momentum, P equals mv. Let's do some basic calculations just to get a little bit comfortable with these formula. So we're going to look at, okay, we're going to look at these ones here. So firstly, oops, I'm going to change one thing here. Sorry, forgive me. I'm just going to change one thing here. What I'm going to do is I'm going to fix these here. If you wouldn't mind, you can probably still see this even though I'm doing this work here, could I get you to copy, to give the top one a try? You guys should be able to do this super easily because, you know, you're not fools. You guys have done math. You guys have done this stuff before. I reckon you can calculate that top one on your own. So just to calculate the top one and maybe the second one too. The second one, I would like you to calculate it in kilogram meters per second, just because it's going to make our lives a lot easier down the track. I realized that in this bottom question, the reason I'm fixing it is because I accidentally said the electron was moving faster than the speed of light. I'm like, well, someone's going to point that out and they're going to be like, sir, are you aware that you made your electron move faster than the speed of light? I'm going to be honest with you, I haven't actually. I should have properly done the research about how fast electrons can move, but I'm like, at least now it's not faster than the speed of light. So we'll go with that. So we're going to do some basic calculations here. So let's give it a crack. So a shopping cart has a mass of 31.75 kilograms. It's moving at 3.4 meters per second. What is its momentum? There's no question mark. That's okay. We can just do this. P equals mv. The mass is 31.75. The velocity in this case is 3.4. That gives us 31.75 times 3.4. Gives us 107.95 kilogram meters per second. It's got some ugly units, but they at least make sense. The units make sense. It's mass times velocity, so the units are a mass unit and a velocity unit. Now this next one, you could probably do it as just a mass unit or a velocity unit, but we're going to do it properly. A 4-ton truck is moving at 60 kilometers an hour. What is the momentum? Well, 4 ton, that's going to be 4,000 kilograms. And 60 kilometers per hour, I think that comes out to be about 16 meters per second. I've started to memorize this because I just use it so many times. I just still think is a, 60 divided by 3.6, 16.6. So we're going to go with maybe, we're with 16.7 meters per second. So therefore our momentum P equals P equals mass times velocity equals 4,000 times 16.7 equals times 4,000. Whoa, 666, the devil's number, 666,607 kilogram meters per second forward. Why are you running forward, sir? Because I asked for a momentum, so I better give a direction. And I probably should have put a direction in these questions. And then this last one, an electron has a mass of 9.13 times 10 to the negative 31 kilograms. It's moving at 4.7 times 10 to the power of 8 meters per second. What is its momentum? P equals mv equals 9.13 times 10 to the power of negative 31 times 4.7 times 10 to the power of 8 equals 4.7 times 10 to the power of 8 times 9.13 e to the negative 31. 4. I'm going to be lazy here, ladies and gents, if you don't mind. 4.3 times 10 to the power of negative 22 kilogram meters per second forward. I'm just going to write another direction. even if it's just forward, just because I want to give a direction, just in case. That's important. It's always good to be doing that anyway. So there's 3 quick and easy calculations about how to calculate momentum. So momentum is not that difficult to calculate. You just go mass times velocity. It's actually one of the easy ones to calculate because if you think about it, it's only got like 2 variables. Like you only got mass and velocity. You only got 3 things. It's as easy to calculate as F equals ma because there's only like 3 things you need to worry about. Now, was there anything in chat? Nope, we're good. So let's move on. Let's move forward then to talking about, well, what's so useful about momentum? I've already said it's a great way to talk about motion. We said the motion is also not just how quickly something moves, but with what kind of push does something have with how quickly it moves. And so, well, what's another good thing that you can do with momentum? It's got mass in it, so there should be some interesting things. There is an interesting idea with momentum. Momentum is conserved. Momentum is always conserved. It can be passed from one object to another object or to many objects, but overall the momentum at the start and end must be the same. And this is actually the law that we're going to use a lot to help us to explain the universe. This helps us to, what I love about this idea of momentum is it gives us a way to calculate how things will move before and after a collision. If you think about it, what we've talked about so far, and this is actually, what we've talked about so far with all of motion, is we've talked about one object, and we've sometimes talked about 2 objects interacting. Like, we've only recently started talking about 2 objects interacting. When we talked about Newton's 3rd law, we said the action-reaction pairs. And then when we started to talk about connected bodies and incline, and when we started talking about connected bodies, we started to talk about, well, what happens if 2 objects interact with each other? Well, this takes it to a new level. The conservation of momentum gives us a way to talk about, well, how does not just the forces apply, but how does the motion, how does the velocity apply? Newton's cradle is an excellent example of momentum. I always like to use Newton's cradles when we discuss momentum because ultimately this ball has a mass and a velocity, and it's able to pass its momentum through all of the other balls until the last ball gets the same momentum and therefore moves at the same speed because it can pass its momentum from one object to another object. And momentum, of course, comes up a lot, and this is also where we would start to do some experiments if we're at school, got to do with momentum. Now, we're going to do some of those calculations now, but I'm going to do them in a sec. I'm going to change the slide. Are we all cool if I change the slide? Is that all right? I'm hearing no yelling saying no, so I'm going to change the slide. But to do that, I'm going to turn off the PowerPoint. And because, of course, I've run out of slides. So we're going to talk about a brand new slide. And this new slide is going to be titled, we're going to deal with, we want to deal with, let's deal with sticking collisions first. Now, we're going to talk a little bit about what happens, and then what we'll do is, we'll deal with sticking collisions first, and then we'll deal with passing momentum. And then the last, if we get time, which I don't think we will, I want to talk a little bit about maybe bouncing collisions. And all of these are then, we're sort of talking about collisions. And that's because when we talk about momentum, it makes sense to talk about two objects interacting. The easiest way to talk about two objects interacting is if they just collide with each other. These are going to be our basic ideas here. Now I'm going to sketch all of these on the actual with my pen rather than trying to create some images and then show you guys. But we're going to start with a sticking collision. What we're going to do is we're going to imagine that we've got two carts. We're going to have one cart here. We're going to say this cart is, we're going to call this 2 kilograms. And then what we're going to do is we're going to get a new cart. And I'd love you guys, if you could draw this down as we go as well. We're going to make this one a little bit smaller. We're going to make this cart a 1 kilogram cart. But what we're going to do is we're going to put maybe some, we're going to put some glue on this cart here. And what's going to happen is this cart here is going to move to the right. It's going to crash into it's going to crash into that stationary, not moving glue cart, and then they're going to get stuck together. And when they get stuck together, let me try that again. They're going to start moving. The reason it's stuck together is because of this glue. They're going to start moving at a new speed. And so what we're going to do today is we're going to now look at this speed here. And what we're going to do is we're going to try and figure out what this new speed is. And so what I'm going to start off by asking you guys, I'm going to ask you guys in the chat, and I want to get at least 5 answers before I start doing this question properly. After they stick together, do you think their speed is going to be slower or faster? What do you guys think? Do you think they're going to move slower or faster together? And this is not based on any calculations. I just want you to intuitively guess. If you had this situation, if you imagine you had 2 carts, they rammed into the other one, they started moving. What do you think would happen? I want to get some guesses. All right, I got one guess. It's a private guess. Private guess for saying slower. Phuc Le has openly said that they should move at the same speed after they collide. Okay, cool. Who's got, and that could have been a trick question. It could be a trick question. So they could move at the same speed, but I want to get some more guesses. What do you guys think? Slower, faster, same speed. What do you think? After they get stuck together, which are they going to move faster, slower, or same speed? Give me a vote here, ladies and gents. Got another guess from Imran saying slower. Yep, okay, so I've got 2 guesses slower. I want 2 more guesses and then I'll move on. So I've had 3 guesses so far. Give me 2 more guesses. Even if you don't have no idea, if you just want to give me a guess, that's what I want. I've got Brendan saying slower. All right, good. That's 4 guesses. I want 1 more guess. Slower or faster? Or same speed? If the force is higher, then faster. If the force is slow, then slower. Well, then what if I told you, Kelvin, there's going to be no force? We're just going to be moving at a constant velocity. Does that change your answer? Speed stays constant. Okay, cool. So I've got 2 people saying the speed should be the same and 2 people saying the speed should be slower. Now we're going to remember that momentum is conserved. Okay, and we're going to calculate this. We're going to calculate this time. We're going to say that the cart initially, we're going to say that it's moving, we're only going to time this very first one. We're going to say this cart is moving at, let's say, 10 meters per second. We're going to make it nice and easy here. Okay. So how do we do these types of calculations? Well, what we would do is we're going to look at the P, the initial velocity at the start is going to equal the final velocity at the end. Okay? Now the initial velocity at the start is going to be the velocity of the red car, is going to be the velocity of the red car, plus the velocity of the blue one. Sorry, plus the momentum of the blue one. Forgive me. Plus the momentum of the blue one. That's going to equal the momentum of the combined. That means that the momentum of the combined is going to be mv, which is whatever its velocity is. And m, we know, is 2 plus 1 is 3. So that's how we could do the calculations. We know the mass. We don't know what speed it's going on. What about the momentum of the red car? The momentum is 2 is mv, happens to be 2 times 10. And the momentum of the blue one, can anyone tell me if this car isn't moving, then what's the momentum of this cart here going to be? Someone take a guess in chat. I'm saying guess because I don't expect you guys to be able to do this yet without too much help. But what's the momentum of the blue one going to be if it's not moving? Zero. Yeah, Roshan, 100% correct. Its mass times its velocity. It's going to be 1 times 0. So what that means is that our initial velocity to the left is going to be 20 kilogram meters per second, whereas its momentum at the end will be 3 times v. Now, if we know the momentum has to be conserved, your final velocity, your final momentum must be equal to your initial momentum. In other words, you can't lose momentum just to nothing. That means that 20 equals 3v. If we know that 20 equals 3v, 20 divided by 3 equals v. V is going to equal 20 divided by 3 is about what? 6.6. So we're going to call this 6.7 meters per second to the right. And that is our final momentum, our final speed, sorry. And that reason that it's going that fast is because it is going, the reason it's going that fast is because it's combined together. Now, here's the question. Is that final speed slower, faster, or the same as the initial speed? Someone answer me. Come on. Is that final speed of 6.7 meters per second slower or faster than the initial speed of the red car? It's slower. Exactly, Kelvin, is slower. And that's because that final object has a larger mass. I want you now to think of a real world example of this. Imagine that I have a soccer ball, and that soccer ball, well, soccer ball is a bad example, but we'll stick with the soccer ball anyway. Oh, yeah, we'll stick with the soccer ball anyway. Let's just say I kick that soccer ball and it hits you straight in the stomach. Now, your combined momentum of the soccer ball plus you, it's going to push you backwards. But now that soccer ball that was moving quite quickly now has a much larger mass. So it's going to move slower because it's combined together. So in the end, it's going to move slower. And that's how we deal with, that's what sort of momentum helps us do, is it helps us understand what physically would occur. And so what we need to do a fair bit extra exploration of momentum, ladies and gents. We really need to explore what happens if those two objects didn't stick together, what might happen. We need to explore what might happen, and we need to talk about a couple of new concepts. But that should give you a bit of a taste of what momentum is. Momentum is a way of measuring the motion of an object. And when we say motion of an object, we're not meaning just how quickly that object is moving, but also with how much effort it's moving because of the mass. And if something crashes into something else, momentum is conserved. The speed times the mass of the end must equal the speed times the mass at the beginning. Ladies and gents, that's it for us, our lesson today.